Okay, so in the third section of hydrostatic chapter, we're just going to look at the force on plane, which is vertical immersed surface. Imagine we had the hydraulic structure here, flat gate, for example, in this case, which is hinged about this point, a top point, and there's a sewer on the left-hand side. On the right-hand side is river, and the river like the push and put like the pressure from outside of the gate, and from the inside we have the sewer, and there's a pressure from inside. Let's just analyze the pressure from the outside, from the river side. So we learned that the pressure is linearly changes, and we just have like a pressure here with a specific amount depending as a function of the depth of the water. And at the bottom, we have another type of the pressure here. And the gate, imagine, is like the rectangular. So this is like the depth is D and the width is L. And the G is the center of that in the middle of the like the depth of the gate. So imagine we have the situation like this. So in that case, pressure at the top of the gate is pressure is equal to rho GH1. So the pressure at the top here, rho GH1. And the pressure at the bottom of the gate is the rho GH2 at the bottom of the gate is here. The pressure is equal to rho GH2 or rho GH2. We're just gonna write it here. So we're just gonna see here the linear increase of the pressure. That's sort of like this trapezoidal distribution of the pressure here. And if we're just gonna use the like the average pressure to see the average pressure of the whole acting the whole gates from outside is the average of the values here. So we have the average of these two pressures. We're just gonna write it down here. And if we're just gonna calculate the force, we learn the force is equal to the pressure times the area. So the pressure, this term inside the bracket, times the area of the gate, which is D times L, okay? We're just gonna keep the letter A for the area. So we're just gonna write it here. If you factor rho G, we just have like the average of the H1 plus H2 divided by 2 times A. And the average of H1 and H2 is equal to the point in the center. Average of the H1 and H2 is the Hg, okay? So we can just write the force is equal to rho GHA times A. So this is the one way of calculating of the pressure. The other way, or the second way of calculating of the pressure, we're just going to go through in here, for the rectangle, like the shape, like this one. So we just know the like the average of the pressure at the top and the bottom, H1 and H2. We can just write H1 plus H2 divided by 2. And the depth to the center of the area, we can call it the vertical depth to the centroid. So this is the vertical depth to the centroid, and we can denote it by Hg. So the average of H1 and H2, we can call it the centroid, or the vertical depth of the centroid. So the vertical depth of the centroid is denoted by Hg. If we know that vertical depth of the centroid, we can calculate the pressure of that point and just multiply by the whole area of the surface, immersed surface, to calculate the force. So the resultant hydrostatic force in this way can be easily calculated by the pressure at the centroid, rho GHG, times area, which is the area of the like the gate, times the area. In that case, force will be equal to rho GA, or A, which is equal to D times L. So that's the way that we just calculate the force. You can just use either this way, calculate the pressure at the top and bottom, take the average of the pressure times the area, or you can just calculate or find out where is the centroid and the vertical depth of the centroid, G or Hg. You calculate the pressure at the centroid, which is rho GHG, and then times the area. So you can either use this way or this way. Both of them are acceptable. So this is the force on plane vertical immersed surface.